All right, I'm going to go over the answers to the final exam review. So I think I'll record this in two parts. I'll do the first 11 or so problems in one video and then the rest in the second video. So this first question here that we're looking at, familiar territory, we've got some data for some trials and we're trying to figure out the rate law and the rate constant for the reaction. So to start out with, we can find the two runs where A is staying the same, the two runs where B is staying the same, and then we can kind of evaluate what's taking place. So now from run 2 to run 1, we see the amount of B doubles, and the rate goes up 4 times. And then from run 2 to run 3, A doubles, and the rate also goes up 4 times. So independently, we can see that the rate is varying as the square of the concentration. So we should be able to say that the exponents for both A and B are 2. So it should be rate equals K A squared B squared. Then it says, what is the overall value, what is the value of the rate constant for this reaction at room temperature? So we'd isolate for K, which would give us K equals rate over A squared B squared, and we can just take the data all from one run. So let's just take the first one, so it would be 2 over 5 squared times 4 squared. And when I solve for that, I get 0.005. All right, second one looks like another kinetics problem. Now it says the second order reaction has a rate constant of 0.005. If the initial concentration of A is 2.5, how long will it take? So we're solving for a time for the concentration of A to become 0.2 molar. So this is second order, which means 1 over the concentration of A at time t equals 1 over the concentration of A at time 0 plus kt. And we're solving for t in this case. Let's plug in the numbers that we have. So it's 1 over 0.2, the concentration at time t, equals 1 over 2.5, the original concentration, plus K, our given rate constant, 0.005 T. So I should be able to tidy that up pretty quickly. 1 over 0.2 would become 5. 1 over 2.5 would become 0.4, and that equals 0.005. Oops, I messed that up. There should be a plus sign, right? 0.005 T. So that becomes 4.6 equals 0.005 T. So then dividing both sides by 0.005, we find out that T equals 920 seconds. Okay, more kinetics. Now it's talking about a first order reaction instead. Now it says in the first order reaction, A makes B, concentration of A is reduced to 10% of its original value, so that's important. Reduced to 10% of its original value. Determine the rate constant for this reaction. So first order means natural log of the ratio of A at time t divided by A at time 0 equals negative kt. So it tells us the time of 5,000 seconds, and it tells us the change in the concentration. So the reduced to 10% means I can replace the ratio of the concentrations by 0.1, and then I have the k value. So natural log 0.1 equals negative 5,000 K. And so when I get the natural log of 0.1, that's negative 2.30. And that equals 5,000, negative 5,000 K. So now we can just divide both sides by negative 5,000, and that'll give us K. So I get, looks like 4.6 times 10 to the negative 4 as my rate constant. And then in the second part it says what is the half-life of A for this reaction. Well, remember the half-life is just the natural log of 2 divided by the rate constant K. We've got that value from the previous part, so. And when we solve for that, it looks like I got 1,500. So our half-life is 1,500 seconds. Okay, I think that's it for the kinetic stuff. Now we're moving on to equilibrium. So here it says, given the reaction below with the given equilibrium constant, if the concentration of A and B at equilibrium are 0.005 and 3.5 respectively, what is the concentration of C at equilibrium? So what we know is K equals, and I'm just going to write it as 4,200 so we're clear about the number, and nobody has a coefficient, so it's just B times C divided by A, products over reactants, and in the first part it's asking us to solve for C given the equilibrium amounts of B and A. So this becomes 4,200 equals 3.5 times the concentration of C divided by 0.005, which is the concentration of A. So let's do that division. So this becomes 4,200 equals 700 times the molarity of C. So dividing both sides by 700, I get C equals 6 molar. Okay, so that was given the equilibrium constant and information at equilibrium, figure out the missing information. The follow-up question here is actually an ice table problem instead, so we can take a look at that. So now I'm given the initial amount of A, and I need to figure out the equilibrium concentration. So here's my reaction, right? A makes B plus C. And initially we can assume no product since it didn't tell us otherwise. A is 2. The change in A will be minus X, change in B will be plus X, change in C will be plus X, so it should be X, X, 2 minus X. So then I should get X squared over 2 minus X equals my equilibrium constant, which is 4,200. From there, let's see, I'll get X squared equals 8,400 minus 4,200X. Rearranging, I'll get X squared plus 4,200X minus 8,400 equals 0. We're just going to have to solve it as the quadratics. Let's do that real quick. So this should become X equals negative 4,200 plus or minus 4,200 squared plus 4 times 8,400, right? C is negative and A is 1, so that simplifies things a bit. Divided by 2 times 1. So let's see what we get here. Let me solve what's in the square root. And that's 4203.99. 998 divided by 2. So we'll only worry about the positive root here. It looks like it would be 3.998 divided by 2. And then I get 1.999. And that makes sense, right? Because a large equilibrium constant, therefore we end up with a large value for x to say the reaction makes a lot of progress. So A then would be 0.001, and then B, the same as C, would be 1.999. All right, so that's what's going on there. 5, it says, consider the endothermic reaction shown below. So let's remember that it's told us it's endothermic. That will be important. What can be done to force the equilibrium to the right? So we could either increase the amount of reactant or decrease the amount of product. Any of those would cause a shift to the right. And then it says, how could we make it go to the left? By doing the opposite, reducing the amount of reactant or increasing the amount of product. Now it says, what will happen to the equilibrium position if the reaction is heated? So we can go back to the original, and since it's endothermic, that means heat is essentially behaving as a reactant. So if I'm heating it, I'm loading up the reactant side, and we'll have to use up that heat that I've added. So we should expect that the equilibrium will shift right to consume the heat that we've added. All right, so that was just some basic Le Chatelier principle questions. I guess that's technically all the exam 1 stuff. Now we're moving on to talking about acid-base stuff. So this is number 6. Solution has an H plus concentration of 3.5 times 10 to the negative 5. Determine the pH. So pretty straightforward here, right? pH is the negative log of the H plus concentration. So that's negative log of 3.5 times 10 to the negative 5. And for that I got 4.46. Number 7, it says determine the pH of a 0.05 molar solution of NaOH. So in reality, that means it's 0.05 molar OH minus. So probably the best way is to get the POH and then take the pH. So the POH would be the negative log of the OH minus concentration, and that's the negative log of 0.05. So from there, we'll get a POH value of 1.30. So that means pH is 14 minus 1.30. So it'll be 12.70. Okay, on to number 8. Looks like an ice table problem with the equilibrium constant and molarities. Because of the low molarity of the original solution, it's probably unlikely that the approximation method will work, so we're probably going to have to solve this the long way. So if here's my acid HA makes H plus A minus. it's 0.0025, 0, 0, minus x plus x plus x. And so it becomes 0.0025 minus x, x, x. So we should get from this x squared over 0.0025 minus x equals 1.8 times 10 to the negative 5. So we can cross multiply and rearrange this, and then we should get our quadratic x squared equals 4.5 times 10 to the negative 8. That's 0.0025 times 1.8 times 10 to the negative 5 minus 1.8 times 10 to the negative 5 x. So rearranging into the correct form, x squared plus 1.8 times 10 to the negative 5x minus 4.5 times 10 to the negative 8 equals 0. So we can solve this with the quadratic formula. So we get x equals negative 1.8 times 10 to the negative 5 plus or minus b squared, so 1.8 times 10 to the negative 5 squared, minus 4ac, but c is negative, so it'll become plus, and a is 1, so it'll go away, 4.5 times 10 to the negative 8, all divided by 2. So x is negative 1.8 times 10 to the negative 5. Let's figure out what's in the bracket and the square root here. And I got 4.25 times 10 to the negative 4. All divided by 2. And we're going to want the positive root again. Let's see what I get here. Looks like I got 2.035, so we'll call it 2.04 times 10 to the negative 4. Oops. 2.04 times 10 to the negative 4, and we know that's the H plus concentration. Kind of out of room here, but let me just write the pH answer right here, the negative log of this number. I get 3.69. Let me rewrite that, 3.69. That'll be our answer to this one. So we really couldn't use the approximation method really because that initial molarity was so low. You could have checked to verify that, but it's been pretty clear to me from the start that it wasn't going to work, so I went ahead and did it the long way to begin with. All right, let's see, number 9. We've got a base with a given Kb value and an initial an initial concentration of the base, and we want to figure out the pH of the solution. Again, this looks like one where I probably can't do the approximation because of the low initial molarity of my base. Okay, so let's see what we have here. So here's our reaction, right? Base plus water makes the conjugate acid HB plus OH minus. And we can ignore water, and then we're told the initial is 0.005, 0, 0 for both products, then minus x plus x plus x. So 0.005 minus x for the initial, and then x and x. So this will give me x squared over 0.005 minus x equals kb, which is 3.5 times 10 to the negative 4. I can cross multiply, then rearrange. So I get x squared equals 1.75 times 10 to the negative 6 minus 3.5 times 10 to the negative 4 x. Rearranging into the correct ax squared plus bx plus c form, I get x squared plus 3.5 times 10 to the negative 4 x minus 1.75 times 10 to the negative 6 equals 0. So now we're pretty much ready to solve our quadratic equation. So x equals, let me scoot over so I have more room. X equals negative b, which is negative 3.5 times 10 to the negative 4 plus or minus b squared minus 4ac. So 3.5 times 10 to the negative 4 squared, and it'll be plus, since c is negative, plus 4 times 1.75. Yeah, let me just clean this up. Sorry about that. All right. X equals negative 3.5 times 10 to the negative 4 plus or minus 3.5 times 10 to the negative 4 squared plus 4 times 1.75 times 10 to the negative 6 all over 2 times 1. Okay, so let's clean that up a bit. I'll figure out what's in the square root. And that becomes 2.67 times 10 to the minus 3. All divided by 2. If we just want the positive root, we can figure that out. And I got 1.16 times 10 to the negative 3. And remember, this represents the hydroxide ion concentration. So now I'll get the POH, which will be the negative log of 1.16 times 10 to the negative 3. And for that, I got 2.94. So then pH equals 14 minus 2.94, and then we should get 11.06. Was our final answer there. Okay, I think 2 more acid-base ones. I'll do those, and then I'll cut off this video and then solve the rest of them in the next half. Okay, next question says a buffer is prepared that is 0.65 molar acetic acid, 0.25 molar acetate. Given the Ka, what is the pH? So we know this is a Henderson-Hasselbalch problem. pH equals pKa plus log base over acid, so A minus over HA. We pretty much have everything we need except for the pKa, so let's get that. pKa is the negative log of Ka. The given Ka is 1.8 times 10 to the negative 5. So pKa is 4.74. So now we're pretty well set because it'll be pH equals 4.74 plus log of, and it's base over acid, so 0.25 is the base, and 0.65 is the acid, right? Acetate over acetic acid. And then I can figure this one out, 4.74 plus the log of 0.25 divided by 0.65, and that's 4.33. That's our answer here. The next one is almost the same, except it's telling me about the Kb value, and it's ammonia and ammonium. So I'm going to need to change the Kb to Ka, then get the pKa value, and then I can figure this one out. So Ka equals 1 times 10 to the negative 14 over Kb, which is 1.8 times 10 to the negative 5. So for this, I get a Ka value of 5.6 times 10 to the negative 10. So this Ka value is talking about the acid, ammonium. We know that's the acid because it has the spare H+. So now I can get the pKa value. And that's going to be the negative log of 5.6 times 10 to the negative 10. And that's 9.25. So now we can plug into Henderson-Hasselbalch. pH equals pKa, 9.25, plus log of base over acid. So that's ammonia over ammonium. So it'll be 0.15 over 0.55. Let's see what we get for that. And I got 8.69 as my pH here. Okay, so 12 and 13 wrap up the exam 2 stuff. So I guess I can go ahead and do those, and then we'll save the exam 3 in later for the second half. So now we're talking about KSP values, and it's telling us about our salt mx2, and it's asking for the molar solubility. So if we're talking about mx2, we can imagine it's breaking apart into 1 mole of M, we'll call it 2 plus, and 2 moles of X, just based on the coefficients. And that means X moles of M2 plus and 2X moles of X minus are being released. And so when we think about the KSP, it'll be the molarity of M2 plus times the molarity of X minus squared. So that becomes X times 2X quantity squared, which makes 4X cubed. And it's asking for the solubility in moles per liter. That's what X is. So now that I know KSP equals 4X cubed, I can solve for X, given that KSP is 2.5 times 10 to the negative 7. So that gives me X cubed equals 2.5 times 10 to the negative 7 divided by 4 is 6.25 times 10 to the negative 8. And so then I can take the cube root of that, and that gives me 3.97 times 10 to the negative 3. Or I guess really I should call it 4.0 times 10 to the negative 3. And that's our molar solubility. Okay, the next one is the reverse of this, where I'm given the salt solubility and I need to find KSP. This time it's mx3 instead. So now it's a 1 to 3 ratio, so we can imagine it breaks into m3 plus and 3x minus. So now if x moles of the cation are released, 3 moles of the anion are released. And then again, following the same pattern, that means KSP equals m3 plus times x minus cubed. Remember, this is one of the things I said a lot, is if there are coefficients in the balanced equation, they'll show up once in the ice table and then again as exponents. That's what we're seeing here. So this becomes x times 3x quantity cubed. When we tidy that up, it becomes 27x to the fourth. So now, knowing that KSP is 27x to the fourth, in this case, I plug in x and solve for KSP. So KSP is going to be 27 times 2.3 times 10 to the negative fourth raised to the fourth power. Let's see what we get here. I got 7.56 times 10 to the negative 14 as my answer here. Okay, so that covers us through